Hello everyone, this is Dr. Srinivasulu, Assistant Professor, Department of Electronics and Instrumentation Engineering, VJEC, Hyderabad. In this video, I am going to explain about the combination of measurement errors. And in the last video, we have already explained about the combination of errors when the parameters or quantities are having summing or difference relation and the product relation. Now in this video, I am going to continue the combination of errors with the remaining cases. In that, the first one is the quotient of quantities. Means when the measured quantity is related to the two or more parameters having the quotient. Like y is equal to u by v relation. In this case, to get the relationship between the limiting errors of the two quantities u and v on the final measured value, we'll derive the relation by taking the log on both sides. Take log on both sides. Then we'll have log y is equal to log of u by v. Now take the differentiation on both sides. We'll get d by dy of log y is equal to d by dy of log of u by v. The differentiation of log y is equal to 1 by y, and here log y, log u by v is written as log u minus log v. Now the differentiation gives 1 by u du by dv du by dy minus 1 by v dv by dy. Now take the common 1 by dy here. The remaining is du by u minus dv by v. When we take this dy to the left hand side, we'll get dy by y is equal to du by u minus dv by v. And this is the relation between the two parameters and the final measurement. So the relation shows the difference of two parameter limiting errors gives the final measured value limiting error. Now we'll see the last case, that is when the two quantities are having the power of a factor or composite form. Like y is equal to u power n into v power m. In this case, similar to the previous case, you will take first the log on both sides. Then we get log y is equal to log of u power n into v power m. This log gives log of u power n plus log of v power m. This is nothing but n log u plus m log v. This is equal to log y. Now take the differentiation on both sides. We get d by dy of log y is equal to d by dy of n log u plus m log v. This is equal to, the differentiation of log y is 1 by y, and the differentiation of n into log u. Here n is constant, so we can take it out from the differentiation, and the differentiation is applied only for log u. So log u differentiation is 1 by u, and since it is differentiated with respect to y, not u, so it will be du by dy. Similarly, for this second term, it will be m into 1 by v into dv by dy. Now we'll take common 1 by dy from RHS side. So it is 1 by dy into n into du by u plus m into dv by v. This dy will take to the left hand side. Therefore, it is dy by y is equal to n into du by u plus m into dv by v. This is the final limiting error of the measured value y. And this is the relation between the two parameters u and y when they are having the power of a factor or composite factor. It is simply the individual limiting errors are multiplied with this power factor and got summed up, then giving the final measured limiting error. Yeah. This is about the error combination of measurements. To understand this power of a factor or composite factor, let us see one example which is mostly or commonly we come across in the electronic circuits, that is the calculation of power when you know the current passing through the resistor. It is expressed as basically power dissipation across the resistor. P is equal to P I square into R. Here I is having the power factor of 2. So for this, to get the limiting error of power, we take first the log on both sides. Therefore, we get log P is equal to log of I square into R. This log, when we divide, this will be log I square plus log R. Since power is 2, we'll have 2 into log I plus log R. This is log P. Now take the differentiation on both sides. Differentiation on both sides. Then it is d by dp of log P is equal to d by dp of 2 into log I plus log R. This is equal to 2 into d by dp of log I plus d by dp of log R. Then this is equal to, Since the differentiation is happening on the power variable, because it is the final measured quantity, we need to differentiate the each individual variables with respect to the final measured quantity P. This differentiation of log I with respect to P will become 1 by I into di by dp. Similarly, for R resistance, so it is plus 1 by R for the differentiation of log R, and since it is with respect to P, this is dr by dp. Now this can be written as, since dp is common in the denominator of both the terms, we can take it common. So 1 by dp into remaining is 2 by I into di plus here 1 by R into dr. This dp, when we write to the left side, before writing to the left side, let us also take the differentiation on the left side. D by dp of log p. Here the log p is differentiated with respect to the same power quantity, so it will be simply 1 by p. Therefore, now we send this dp to the left side. We will get dp by p is equal to 2 into di by I plus dr by r. Here delta R by R is the relative limiting error of the resistance, and di by I is the relative limiting error of current. So these two quantities are summed up, and here the current is multiplied by 2, then summed up with the resistance relative limiting error, and giving finally the limiting error of the power. This is the way the limiting error of the two individual quantities affecting the limiting error of the final measurement. Thanks for watching the video.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.